Now we're going to consider some problems using the concept of impulse. Impulse, as we saw in class in our little demo, is the product of force times time. So impulse is a force applied over a period of time. And we saw that the impulse is equal to the change in momentum of a single object. Impulse problems are approached a little bit differently than conservation of momentum problems, because in an impulse problem you usually consider one object, the one that's changing momentums, to be inside the system, and something else is outside of the system applying a force to that object. These can't be conservation of momentum problems because now there is a net force on the system. So in this problem, we've got a ball that's being hit by a bat. The ball is the thing that's moving that we can really talk about momentum for. So that's what we're going to put inside the system. And the bat is going to be outside the system, providing an impulse, a change, a force applied over time to the ball. So a ball comes into a bat at a velocity of negative 20 meters per second. So before, or initially, the ball, which has a mass of 0.2 kilograms, has a velocity of negative 20 meters per second. And so the momentum beforehand, 0.2 times negative 20, is 4. Negative 4 kilogram meters per second. And it says that the ball hits the bat for 0.01 seconds and leaves the bat with a velocity of positive 30 meters per second. So afterwards, the same ball with the 0.2 kilogram mass has a velocity of positive 30 meters per second. So it's left the bat going the opposite direction. Now it's going forward. So the momentum afterwards is 30 times 0.2, or 6 kilogram meters per second. So impulse, the force applied over a period of time, is equal to the change in momentum. We can calculate the change in momentum by taking that little triangle. Delta always means final minus initial. So in this case it would be 6 minus negative 4. And that change in momentum is equal to the average force times the time over which the force is applied. We do not know the average force. That's what we're being asked to solve for. But we do know that the bat was in contact with the ball for 0.01 seconds. So 0.01. So the force, the average force that the bat applies to the ball, is equal to 10 divided by 0.01, which is 1,000 newtons. So you can think about this as the bat is transferring momentum to the ball. So, and momentum is going into the ball. And the average force that the bat applied to the ball was 1,000 newtons. As a reminder, if the bat hit the ball with 1,000 newtons, the ball also hit the bat back with 1,000 newtons. That's Newton's third law, so you don't want to forget about that. In this second example, we're going to look at how you tell the difference between when you want to use conservation of momentum to answer a problem and when you want to think more in terms of impulse, one object in the system, one out. In this first part of the problem, we've got Bozo catching a bowling ball. And we've got two objects. They're both moving. We know velocities and masses for both of them. So since I've got information about both, and there's no mention of time or force in this problem, this is looking more like a conservation of momentum problem, because conservation of momentum is really only going to involve masses and velocities. So because I want to consider conservation of momentum, I want to keep in mind that the net force in the system is 0. Since Bozo's on ice, that's a pretty good assumption. And we want to put both objects in the system. We want the ball and Bozo both in the system. So we're going to make a momentum bar graph for both the initial and the final momentum. Before the ball is caught, The ball is moving forward with a velocity of 10 meters per second. And it has a mass of 20 kilograms. So 20 kilograms times positive 10 meters per second. That ball initially has a momentum of 200. Bozo has been skating backwards, but not as quickly, only negative 2 meters per second, but he has a bigger mass. So his mass is 60 kilograms. His velocity is only negative 2 meters per second, so Bozo's initial momentum is negative 120. So total beforehand, we've got positive 200 and negative 120 for a total of 80, positive 80 kilogram meters per second. Since both objects are in the system and the net force is 0, the total momentum before the collision has to equal the total momentum after the collision. And Bozo catches the ball. So after the collision, they're going to be kind of moving as an object with a total mass of 80 kilograms, 20 plus 60. So looking right away, I can actually solve this problem pretty quickly. If the total mass after they collide is 80 kilograms, and I need the momentum to be 80 kilograms times meters per second, then the velocity must just be positive 1 meters per second. Mathematically, if you want to see the formula, momentum equals mass times velocity. I know that the total momentum of both of them together must be 80. They're moving as 1, and the total they have a mass of 80 kilograms. So the velocity, 80 divided by 80, must be positive 1 meters per second. So by applying the law of conservation of momentum, I have determined that the velocity of the two must be positive 1 meters per second after Bozo catches the bowling ball. Now we're going to look at the same situation, Bozo catching the bowling ball. But now it's asking me how much force is exerted on Bozo if it takes 0.1 seconds to catch the ball. Well, now we're dealing with the situation that's asking about average force and time. Those two variables are involved when we talk about impulse, change in momentum. So an impulse problem, we're going to think about one object in the system. How about the ball? And one object outside the system. We'll put Bozo outside the system. So we want to think about how much the ball's momentum is changing in this story. The ball initially, with a mass of 20 kilograms, is moving forward, positive 10 meters per second. For a total momentum of 200. After the ball has been caught, it still has a mass of 20 kilograms, but we determined by applying conservation of momentum that the ball only now has a velocity of positive 1 meters per second. So afterwards, the ball only has a momentum of 1 times 20, or 20 kilogram meters per second. So the ball started with a momentum of 200 kilograms times meters over seconds. It ended with a momentum of 20 kilogram meters over seconds. So the ball must have lost momentum or transferred some of its momentum to Bozo. Impulse, which is an average force times the time, is equal to the change in momentum of an object. So the impulse that the ball experienced is equal to force times 0.1 seconds, and the change in momentum, final, 20, minus initial, 200. Solving for force, we find that the average force that the ball applied to Bozo is 1,800 newtons. And it's negative because Bozo would have been pushing the ball in the negative direction. So if I look up here in the picture, Bozo is pushing the ball this way. Another question that could be asked is, if Bozo pushed the ball negative 1,800 newtons, how much force did the ball apply to Bozo? Well, by Newton's third law, there are equal and opposite forces when two objects interact, so the ball pushed Bozo forward with a force of 1,800 newtons. And if you had chosen to solve the problem with Bozo in the system and the ball outside of the system, you would find that while the ball lost 180 kilogram meters per second of momentum, Bozo gained 180 kilogram meters per second. So because the contact time has to be the same, one object can't touch another without the second object touching the first, the contact time has to be the same, and by Newton's third law, the force always has to be the same. The change in momentum has to be equal and opposite, just like the forces do. So that wraps up our 2 examples on impulse. Good luck, and it's now your turn to try some of your own.